So today we're going to be talking about democratizing AI for industrial applications and also democratizing AI in general. So I'm Arun Subramanian. I lead data science and analytics for Baker Hughes, a GE company. I just wanted to start off with some challenges and potential opportunities that the oil and gas industry presents. And this is, although the slide is titled as an oil and gas industry-specific slide, this is pretty common for most of the traditional industries that are out there today. Right? Think about the left-hand side of the equation where you have assets, systems, very large-scale critical infrastructure that has been commissioned over the last 30 to 50 years. They're all aging, they're in different stages of aging, different stages of performance, different stages of reliability. They all need to be somehow upgraded and kept alive at 90% or above reliability and availability. Right? To make things more complex, or rather interesting, a lot of the workforce that has kept these systems up and running live and understand these systems well are slated to retire in the next 5 to 10 years. So even if there are enough engineers who will get trained and onboarded into these industries, it's very, very hard for them to come up to speed and fill the gap that these experienced engineers and scientists and developers would leave behind. Right? So there has to be something that bridges the gap between the two. And the cost of any of these systems going down actually is astronomical even today. It's scary to think about what will be the cost 10 or 12, 15 years down the line. The number down there, that is $6.6 billion in unplanned downtime cost, that is just for downstream in North America. Right. So if you look at the unplanned downtime costs across the world, from upstream, that is where you extract oil, midstream where you transport oil, and downstream where you process it and then send it off to gasoline or any of the other petroleum products, that number is in hundreds of billions, if not trillions. Right? Now, that's the challenge part of the story. The opportunity side is on the right side. Now, oil and gas industry has enjoyed very high oil prices for a while, and they also have enjoyed need or growth of need across the board until about 2012, 2013, where the oil price went from $30 a barrel to less than $40 a barrel overnight. And what that caused was a sudden realization that the industry was slightly lacking behind compared to the aviation industry or the power industry or any of the traditional industries. And the need for sudden digitalization, the need for going after something that they've not done, came about very, very suddenly in the industry. And the oil prices have stabilized, they've gone back down and up again. But what it has resulted in is the top right figure that you see there, where most of the industrial companies that want to invest in AI, in any kinds of modern technologies, 75% of the fraction of money that's going to be invested in AI or invested in something analytics is going to come from the oil and gas market. Right? That's partly driven by the need and partly driven by the fact that it was lagging behind for some time. Now they're catching up quite a bit. Right? Now, flip the equation a little bit, and I didn't grow up in the oil and gas industry. I actually grew up in the aviation and power industry before coming on to looking at problems that require analytics in oil and gas. And the first thing that surprised me was the scale and quantity of data in oil and gas. So compare the volumes of data here on the slide here to what you would see in aviation or power. So if you take off from New York, land in London, typically the aircraft or the aircraft engine generates about a terabyte of data. Out of that terabyte of data, you store maybe 100 megabytes. Because it's very expensive to store, very expensive to transmit, and traditionally it's not something that the airline industry has stored. Compare that to the oil and gas industry, where an offshore oil rig, an offshore oil platform, generates anywhere from 20,000 to 30,000 sensors, generating data every 2 to 3 seconds, stored in perpetuity since the day that platform was commissioned, so 20, 30 years. That's a data scientist's bonanza. Right? And if you can actually get to that data correctly and do something about it, that's fantastic. Right? And that's really where the opportunity lies. Now, I also want to pinpoint one thing where analytics means a lot of different things to a lot of different people. Right? What it means to us from Baker Hughes GE and GE in broad is the combination of 3 very important things. Analytics is not necessarily anything new. If you look at engineering, if you look at any kinds of systems where there are large-scale domain knowledge that is required, a combination of domain And traditional software has been around for decades. That's what produces traditional solutions. That's what runs the world today. The new kid on the block is what today is known as the cool parts of data science. Think of your most favorite algorithm, most common buzzword out there, throw it in there, that's data science, combined with a slightly different way of writing software. Modern software on the cloud, automatically scalable, horizontally and vertically scalable. Now, that has also been proven to do some things that are not possible from the traditional solutions. Now, if any of us were told 10 years ago that a system would automatically tell you when to leave this stage today, go home, start at 4:30 so that you can actually get home on time, navigating all the traffic, making sure that you're actually on time to take your daughter to a dance class. Because your calendar knew that your daughter has a dance class, your phone knows that you're here, and it knows to navigate between those two locations. We all would have probably laughed. But that's solved today. Or think of a case where a shop would send you something before you even express the intent that you like that thing. That's also solved. Like Amazon sends you stuff today that you never once liked anywhere. Right? Little creepy, but it's done. And that's the needle in a haystack kind of problem, very, very hard problems to solve. But thanks to the Googles and Amazons and the Facebooks and Apples of the world, they have shown us a way to solve those things. Now, translate that to the industrial domain. Most of the time, the 20,000 sensors transmitting 2 to 3 second data every day for the last 30 years, they just tell us that the systems are fine. Because the systems are designed to be fine for a very long period of time. So if you go looking for something meaningful in that data, you most of the time find nothing. Right? All the data means nothing to most of the time. The one time when the system fails, the one time that something actually goes wrong, you don't have any data about that thing. Right? And that's really what is the problem that we're trying to find, where we're trying to find a needle in an ocean of data, not even a needle in a haystack problem. And most of the time, we don't even know what the needle looks like. Right? And that's the problems we're trying to solve. I'll give you some examples of that. But before I go into that one, I know I introduced myself as the head of data science, but this is a tenet that we believe very deeply in our teams. And this is something attributed to George Box. He said it a long time ago. All models are wrong, but some are useful. Box stopped there. Actually, we go a little further than that. Okay. All models are wrong. Some are useful for a short period of time. Right? And if you believe that very deeply, then you design your systems very, very differently. You design your teams differently. You think about problems and solutions differently. So we don't necessarily go into a problem saying, hey, we are the school data science team. Use domain experts or subject matter experts who've been designing the system and running it reliably for the last 30 years, don't know what we know, so we'll come solve that problem for you. We actually rarely do that. Sometimes we do that and get hit for it, but most of the time, it's this tenet that drives us, and I'll give you the reasons why. And if you think about this carefully, any model that we build, even the most sophisticated deep learning model that you can build on thousands of hours of GPU or TPU compute, this tenet still holds true. So you have to have systems that constantly update themselves, constantly go in, and make sure that they're monitoring your models. So you need models that monitor your models, and then you need more models that monitor your people who build the models. Right? So that is where our concept of digital twin was born. And most of the concept on this slide was born out of pure necessity. Right? So we didn't really sit in an ivory tower, think about this, and said, this is a fantastic way to solve problems. We were actually posed with problems where things like, OK, there's one failure in the field. There's one jet engine that failed. Can you actually tell from that one failure, do you have to take down an entire fleet of engines down, which causes a massive outage in the entire transportation network in the world or not? Safety issues where an offshore oil platform just sent off an alert. Do you shut down the platform, which costs you about $50 million a day if you shut it down? If you don't shut it down, it's going to cause an environmental disaster that's going to go costing about $1 trillion over a period of 5 to 10 years. Those are the kinds of answers you're trying to answer. And most of the time, we don't have data to go about solving that problem. So the concept of digital twin, where the model is a combination of domain, we most often just start with domain, build around traditional machine learning problems that gives us the ability to solve known problems very well. So if I tell you there's a crack, the crack is propagating because of a thermal load. I can give you very, very, very precise models that tell you how the crack is going to propagate under that load. That's the known knowns. Now, if I go one level above and say I don't necessarily know the temperatures that are affecting this particular part, I can measure it to within plus or minus 10 degrees or 20 degrees. That's a known unknown. So that unknown, the known unknown of temperature, I can propagate through and tell you, well, this part is going to fail within the next 10 days with a 90% probability. Right? That's where probabilistic inference comes in. The real advantage of using deep learning for us is where I can't necessarily post the problem in known knowns or known unknowns. Cases where I know that something is going to go wrong, but I don't necessarily know what to go catch. So I'll go back to the 20,000 sensor example. We have 20,000 sensors emitting data every 2 seconds. I have written rules, heuristics, watched all kinds of critical things already. I can catch maybe 90% of the things that are going to go wrong. What about the last 10%? I don't know what rules to write. I don't even know what to watch and how often do I need to watch it for. That's really where deep learning systems come into play. And that's how we actually got into deep learning. And then as we learned more and started deploying these systems more, we realized that it can also tell us when to go update our models. It can also tell us when to go watch what models. Right? So I'll give you some examples of that. But before I go there, I wanted to give you an example of what we think about as scale or systems of systems. So we most of the time look at systems that are very, very large. So that offshore oil platform has roughly about 30 different large-scale systems in that. Each system has anywhere from 10 to 15 large subsystems. Each subsystem has 50 to 100 assets. Okay? An asset would be something like a gas turbine. Okay? For those of you who have not seen a gas turbine, some of the gas turbines fill rooms that are twice this size. So very, very large-scale things that are considered a small asset, and they won't even be described in this particular plot on the right side. And most of the time, the answer or the problem we are trying to solve is, OK, I have data from all of these different assets, all of these different sensors coming in. What is going wrong? I already know to catch 90% of the things that are going wrong, catch the 10% of the things that I cannot catch, I meaning the operator of the actual platform. Right? So what we do is we actually convert the physical system into an information network. So we know already how assets are connected, how subsystems are connected, how systems are connected. The connectivity is what is shown on the right-hand side. So each node there is actually an asset that is connecting to each other. Maybe a pump is connected to a fuel system is connected to a gas turbine might be connected to a compressor, a whole lot of different things. Right? That physical connectivity is shown on the right side. But the colors actually come from the data. So what we do is we take operational data and try to understand purely from operational data, is there anything connected with each other without knowing how they're connected in the physical space. That's the one on the left side. Now you superimpose that onto the right-hand side, you see some interesting things. You start seeing things where most of the systems seem to be connected only with the assets inside that system. So if you look at the blue dots, they're only in the top left and maybe things that are physically connected. But there are some green dots on the top right and on the bottom left. There is no physical connection. There's no direct physical connection. There's not even a second or third order direct connection. Right? But your operational data is telling you that there's something correlated. Now, this could be one of two things. It's the traditional or the classical problem of correlation is not causation, right? Where this could very well be, hey, are you trying to tell me that the S&P 500 index is correlated to milk prices in Bangladesh? Right? You can definitely come up with a data set that tells you that. Now, the proof of this exercise is, can you predict failures that you cannot predict before and reliably, right? And that is here. So we've taken this approach where we combine the physical network with the operational history, connected it together, built models, very large-scale models. I'll tell you about what these models are, and predicted what was not known to us before. So this is a real example where a customer gave us operational data for 2 years' worth of operations of one system. And that one system had about 13 subsystems, roughly 4,000 sensors. That's what they call a proof of concept, about 5 terabytes of data. Right? We built our models. All of these models were a combination of autoencoders, probabilistically enabled, and a system-of-system network model. So all of them combined together to predict a third year's worth of data, trying to figure out if the model can predict things that it hasn't seen before. Right? And the proof is we could successfully detect all unplanned downtime events. The events that we hadn't seen, we didn't know how many events, we just predicted 16 out of 16 events. Now, I could have done that very easily by just saying, let me call everything as an event. I could have caused 1,600 failures, and that would have included the 16 failures that was actually real. So to make sure that a model was not overtuned or just junk or just flipping a coin, we also made sure that we can compare it with the current scenario of how do you catch faults. So we were able to get all unplanned downtime events by reducing false positives and false negatives simultaneously, right? And this one we can do repeatably, and to do this repeatably, we actually have to go through many different pipelines, right? So if you think about this, you got data, you validate the data, you walk through, say, an architecture space, you give it to a data scientist, they say, okay, I know for this particular problem, I can get to a model that looks good. Maybe I'll use a particular type of autoencoder, maybe I use a particular type of LSTM, I'll get a model. And a data scientist's time is very valuable. Usually you build maybe 1 or 2, maybe 3 or 4 iterations, and you stop. That's a typical workflow from the left to right. In our case, because we didn't have the luxury to say, okay, I have a prediction, you will give me the results of a blind validation test, and I can go back and update my models. I still have to go build models without knowing what my validation data set is, or the true test data set is. So we actually had to go build and explore the entire architecture space and come up with models that we know are not just a model, but a very, very good model to begin with. So the way we do it is we actually start with initial samples that you see here. Those are the red crosses, where we say, well, let me go explore the design space and use that to build a Bayesian meta model. So this is a meta model that tells you, okay, if I change the number of layers, if I change the activation functions, do I use regularization or not? That is if you decide that you're going to use some kind of a deep neural network. Or you can also go in and say, let me go build a Gaussian process model. Or I'll just go build a simple linear regression model. All of those are different search spaces that we're searching across. Use it to build a meta model, and then use a genetic algorithm to go optimize all of those different variables simultaneously. So it's a massive optimization exercise that goes from the red dot through all the gray dots to get you to those green Pareto optimal points. Now, typically, you may be used to seeing optimization problems as going up and north. That's to be good. Here, the two objectives are loss functions. So you want it to be as small as possible. So you're reducing loss in different dimensions to get it to very, very small values, right? You get to an objective. To get here, we had to use TensorFlow at its edge. We had to go back and use Kubeflow at its edge, and I'll show you how we did that, and combine all of this with TensorFlow probability as well. Of course, all of these running on NVIDIA and GC containers as well. Right. The nice thing is, to get to a model, we could go explore more than 250,000 architectures very rapidly for one model. Right? So we're just going and building one model here. And the improvement in training from just a random search is at least 10 times. And 10 times is what we can achieve consistently. So you give it to the best data scientists we have on team. They go and find out saying, OK, this model will work for this particular use case. I know I've built it 100 times. Let me go build it. Compared to that, you still come up with architectures that are significantly better. Now, if you flip the question and ask us, do you understand the architectures? Do you understand why something is working? The answer is no. Many times, we actually look at that and say, why exactly is it working? I don't know. And I don't really know if I'd ever picked that particular architecture, but it works in this particular use case, right? And this is for one model. So for the offshore oil platform that I've been talking about, that platform has about 40 systems. Each of those systems would have about 8 of these models. And so the scale you're talking about is significantly high. And to get this to run properly, of course, costs a lot of GPU compute, right? And as most of you probably know in this room, GPUs are reasonably expensive. And running them at this scale can break the bank, right? Now, the general question we face is, are you guys crazy? Do you really, really want to go run this many models at scale? This is the plot we actually use with our CFOs as well. So that's the anomaly detection model on the left side. That's actually at scale from the previous slide. The model that Facebook open sourced just last month on OpenGo, right, the ELF model, that model ran on 2,000 GPUs for 2 weeks. So compared to the scale of operations that we're talking about, where a model saying something wrong can give you an outcome that will get the business to lose tens of millions, if not hundreds of millions, actually is very, very limited. The reason why there's a sticker shock in these kinds of cases is we are not used to building these kinds of models up to this point in time. For these kinds of operational histories, we don't really build these models like that. Today, if you ask us how an offshore oil platform is managed, it's probably managed with a spreadsheet. Right? But what's lost in that spreadsheet calculation is all of the effort that goes in getting a simple answer to the operator. Imagine what the operator can do with a model which will tell you 50 days or 100 days before that something is going to happen and you can change your operations. The financial impact of that is significant. Right? Now, to do all of these things at scale, we do need to orchestrate things very, very differently. So for us, everything runs inside containers. Containers is a first-class citizen. And it's not just that we get to build these cool new models. We also have to live in the world of models that have existed for the last 30 years, which are running reliably. Most of the times, we can't necessarily go recode them or change them. And most of the time, we don't need to change them. Right? So the workflow that's shown here, where you start with a Python model, it goes into some proprietary model, say, for an example, is HYSYS. There's a Fortran model that feeds something into that pipeline that goes into something else that's Python that might actually run a robust optimizer in Go, is actually fairly common for us. We don't necessarily use Fortran 4 that much, but Fortran 77 is something we have quite a lot of. Okay? And that's not just for oil and gas, any industry as well. So you need to be able to run all of these things simultaneously at scale, orchestrated, and get an answer back to the user. Right? Now, the example I showed before, where you actually start with some few red crosses, that's the initial points on the top. There's an actual Kubeflow pipeline that's implemented to run both on-prem as well as on a cloud. We'll show you running this on GCP today. That's the initial model running. After all of those models are run, Kubeflow decides that, OK, let me go build this Bayesian model, and then spawn off yet another set of models after I optimize. That's the second iteration. You keep going to multiple iterations. Finally, you get to an optimal architecture. Right? Now, the data scientist who's building these models does not know much about Bayesian models or even optimization. The optimization expert who knows and understands stochastic optimization does not know what models are actually being optimized. The software architect who makes sure that all of these things run at scale, GPUs, when you require GPUs, actually are available, and all of these things actually are available when a data scientist kicks off a run, does not necessarily understand any of this. You need to be able to orchestrate all of these things together to run at scale. Right? Now, to even get there, we had to make sure that, OK, you can go ask for 100 GPUs or 1,000 GPUs or 100,000 GPUs from GCP. They may give it to you, and it's a lot of money on your side to go get those hardware actually available to you. But do you actually have the software to go load them up at scale? So this is a load balancer that we wrote, and this is a result of a test run where we have two systems competing with each other. Every time the load balancer sees that all of these GPUs or all the resources are consumed, it'll add a node with a GPU. So that's what's happening on the top left. So each time it hits something, you add a node, right? The actual load or utilization per GPU is on the bottom left. Immediately after a GPU node is added, the total utilization goes down. Right? So there is something else that's watching that says, OK, the total utilization has gone down. I actually have more resources. I can reload them back up. So there is a constant tug of war going on between these two systems, where the load drops and it goes back up. As soon as it goes back up, another GPU node is added, until, of course, you hit a point where you can't spend any more. So that's what happens when you hit 10 nodes with 2 GPUs each. So getting up to this level of scaling where you add a GPU node, you get it instantly, your billing starts instantly, but most of the time you can't use it instantly. So you have to be careful about that. Right? And after you're done, you need to be able to shut it down instantly, because billing continues to go. Right? So this one, running the same Kubeflow experiment that we showed before, is what is shown here. So we ran the first experiment, the load spikes on the top left. Then the Bayesian optimization runs, so the load drops. Then the second load goes back up. And the interesting thing that's happening on the bottom right, you can see, is each of the times it hits max load, it actually adds more nodes. And once all of the initial runs are done, it spins it back down way below where it started. Right? And this has to happen consistently across the board, because many times we have 10, 20, 30 data scientists running these pipelines. and we can't necessarily have SREs on standby to keep increasing GPUs or even watching, do you have the ability to run GPUs or not? Right. I'm picking on GPUs a bit here because that's reasonably expensive, but if you use TPUs, it's the same thing. Even not even any compute. If you're using high-performance storage, for example, that can also break the bank. So you have to be very careful about loading at these kinds of scales, right? And there's another example of us showing that we can actually run through all of these architecture steps and keep the GPU utilization at or above 80%. That alone is not a simple problem to crack, right? So when you're thinking about scale, also think about the fact that if you acquire hardware or acquire virtual hardware, you also need software that can scale with the virtual or actual real hardware. Now, how did we get here? The title of the talk is Democratizing AI, and I promise I'll get back to that. Doing all of these things is not necessarily unique for oil and gas. Almost all industries out there are solving one hard problem or the other. And to get to anything at scale, you need more than one or two types of disciplines, right? And we got here by blood and sweat and very hard work by a lot of people in very disparate and different communities, right? So we had data scientists, but lumping all data scientists into one large bucket is also not being that fair to them, right? There are traditional machine learning researchers, there are probabilistic researchers, and also a lot of deep learning researchers working together to get us to where we are today. Domain experts are the folks who told us what to go solve for. So we didn't really go to them and say, give us your easy problems, we'll just make them faster. We actually told them, give us the problems that you can't solve or have not been able to solve, give us your hard problems, and help us understand them to the point where we can at least tell you whether we can solve them or not. And we walked into problems where we had a certainty of maybe 50% to think that we can solve it. And in many cases, it was necessary because those are the problems that could justify the cost of using a system like this, right? And software, again, is not all created equal, right? So we put these specific words here because thinking about software in silos also causes a lot of problems. Most of our software engineers were full stack. They also were very experienced in distributed systems, right? And I'll talk to you about that why. And thinking about cloud native is something we had to learn along the way, right? We started with systems that were completely on-prem and then moved to the cloud thinking, okay, we can more or less modify it a little bit to get to the cloud. Only when we started hitting scales of the problems that we had to solve, we realized that we had to go rewrite a lot of different things. So if you want things to run at scale, be willing to rewrite 30, 40, sometimes 50% of your systems. Okay. So what does democratizing AI mean? Because I thought about this a little bit for this talk, and I've been thinking about this for a while. It means different things to different people. Now, if you're a data science researcher, a data scientist, or a practitioner who's been doing this for many years, when you hear the word democratizing AI, you probably think, OK, I know how to build my models. I have my tools. I'm going to continue doing that. I am very, very good about using and tooling myself. But I don't necessarily know how to make my models available for hundreds, if not thousands of people repeatably. So productionizing a model is probably what people think of when you're a data science researcher or an expert. And by the way, I looked up the word productionize is a word, apparently. OK. If you're a domain expert or a business user or somebody who hears a lot about AI, who's heard about all the buzz, maybe tried something about on yourself, and find that most of the tooling is hard to use, most of the jargon is very hard to understand, and many times you can't connect an outcome that looks nice to the outcome that you care about, then you want to be able to build these models fast and productionize very, very fast, right? Now, if you're a software developer, if you're an applications developer, you may not necessarily care about the specific nuance of an algorithm or a specific nuance of how a model has been reduced to a size that can be scaled and, say, served well. Somebody already did that work. You care more about how do I consume it for the particular use case you have in mind. Now, any of the tool sets out there, any of the tooling out there, people who are building tools for democratizing AI have to cater to all of these three different, very different, say, workloads, right? And we've been doing this for a while, and mostly because of necessity for ourselves, because we are a small team which has to scale to very large problems as well as very, very large scale systems. So we made some very careful choices, right? So being Container first was by necessity, and I'll give you some metrics on what going to containers did to us. So we did come up with a philosophy called depend on Docker. That's the logo for it. Obviously, we like doing things, hence DO, depend on Docker. And everything we run is containerized, except for raw storage. Everything is containerized, right? And we also make sure that that means we have to orchestrate at scale as well. So we'll show you a demo of a model and a set of models running at scale today. But before I get to the demos, just what did it do to us? So like rewind 5 years ago when we were trying to build what we called at that point in time a digital twin platform for GE, we would build a technique, we would build a model that would be in the research phase. Getting that model into production meant that we had to stick to very, very strong, say, quarterly releases. And every single quarterly release would go up to the midnight before the release. And something that was working just fine the day before would break. And most of the time, it was some dependency or other on the model side. And the number of times we heard, hey, this is working just fine on my laptop, or is working just fine on my system, it's something wrong with your production system, just drove us nuts, to be honest. We moved to containers, and 5 years ago, moving to containers was not that popular. We had to still face comments like, oh, nobody would ever let you run containers in our system, to today, where everybody runs everything in containers. It moved the production deployment of a model that has already been validated, taking 6 months, to roughly an hour. So the model has already been validated by somebody. It's a data scientist, a subject matter expert. They agree. That model going from being in their systems to a production system is roughly an hour for us today. Right? Of course, it doesn't always happen in 1 hour every time. But if the data scientist was, say, disciplined enough to use our tooling from day one and actually have everything running in containers, those containers transmitting into our production systems is under an hour. Right? So that's really what going to containers and sticking with discipline got us. Right? Now, the demo use case, I'll show you 2 different types or flavors. The first one is a simple case where I'm just going to take a data set, run it through some algorithms that will detect what is in this data set and tell you what possible models you can build. On a UI, actually, it will build several different kinds of models to get you to a best model. But the same demo will also run and show you that this can scale across thousands of models built live on stage, and there was a promise in the abstract as well. And we'll hopefully, if the demo gods agree today, we'll show the demo working today. To get that to work, we obviously need high-speed storage, but a lot of the core services had to scale as well. And we had to break it down to a point where we can control things at a very fine-grained level. And if you see at the top, we have both GKE clusters and self-managed clusters. And in this particular case, we did that because we were experimenting with things, but it actually came back to save us because the recent update from 1.14 introduced a non-backward compatible change. And that broke our self-managed clusters, but the GKE clusters were up. So actually preparing for this talk, we were fine actually going through preparing as we were upgrading our self-managed clusters as well. Right? So I'll walk you through how to do that. But this is the cluster we'll be showing you, hopefully live running. We have a master node. And what is expanded on the right-hand side is just the master node. The lines are not necessarily correct. So we have 100 nodes per cluster. That's the GKE master cluster. On the top are 5 workload clusters. On the bottom are 5 self-managed clusters. So I'm going to kick off some model runtimes. And that'll actually load all of these different cases as well. So before I go spin up all of those clusters, I just wanted to show you a demo of what a subject matter expert would do if he didn't know anything about what is in the data set. So this is our AI system called AI Factory, where I just come in and drag and drop a data set. Okay. The data set is simple tabular data. As you can see, it just has one header with, in this particular case, I think 5 variables and about 100 rows of data. And this is a data set that we just created to tell you how do you predict a wear and tear of a wheel, depending on how fast you're accelerating in the car, what surface you're driving on, and things like that. So what happened here, it's saying, OK, it knows that it's a CSV file. It wants to see if we can build guided build. Now, going from that first page to here, what happened was it understood what is in the file, and this is granted a small file, but if you had a large file with millions of rows, it'll do the same thing. It understood what are the variables in the file that are numeric, and also went in and said, okay, given that these are the variables you have, these are the potential variables that you can use as outputs in your system. And that means that for each of those outputs, it'll go in and use the rest of the variables as inputs and try and build your best model. And it not only did that, it went back and said, okay, here are all the different techniques in the system that are already preloaded that can be used with this data set. Now remember, if you're a subject matter expert, you don't necessarily know what all of these techniques mean. You don't necessarily need to care. You just got here, the system is suggesting something. Let it continue to go on up to a point where it builds some models, and then you can evaluate if the model is useful or not. That's where you're going with it. Now, if you don't necessarily agree with all the variables that it shows, for example, if I don't want to build a model for friction, but I want to build a model for acceleration, I could do that as well. And then I go in and say, okay, build all 24 models. Now, a couple of things need to happen for this to work, right? Where it needs to take this data set, split that into testing and training, connect it to all of these different techniques, select all the defaults, and then come out with the best models. Now, in the time frame that I just said that, it went in, built all those models live, came back and is telling us what are the best models for each kind of output that the system told us. Now, some of these outputs may not necessarily make sense. For example, I don't necessarily want to build a model for weight, but I want a model for wear, I want a model for acceleration, for example. And it also went in and said, out of the 6 techniques it went and evaluated, for each of the output, it's telling you what's the best model based on a particular root mean square error. Right? It's a simple example. I can run it at scale here on the UI. Now, what if instead of having 6 variables, you actually had 10,000 variables? Or instead of building 24 models, you want to build 10,000 models or 100,000 models. So we have a CLI for that as well. So let me switch to that. And to just walk you through this one, I have 10 cube contexts running on the left-hand side. And each one, so the first left-hand side ones are GKE clusters. So there's GKE 1, 2, all the way to 5. And on the right-hand side are our self-managed Kubernetes clusters. So that's the tower you saw. So the left-hand side is GKE, right-hand side is self-managed. And I'm going to just run a simple watch command. So I'm going to just watch the pods. And most of it is telling you that no resources are found. That means nothing is actually happening there because I have not run anything yet. Right? Now, let me go in here and run the case where I'm actually spinning up the same thing, where we are simulating 10 different users running 1,000 models each. Right? So it's going to spin up 10,000 models simultaneously across all of these different clusters. So if I hit this cluster and hold my fingers. OK, what you're going to see is different colors going through. So each color is one particular Kubernetes cluster. So it's actually loading all of the Kubernetes clusters simultaneously. And what you're going to see is on the left-hand side, each of the clusters actually starting to get loaded. Right? And you can see some of them started. And it's processing, each of the nodes are going to process about 1,200 models. Now, if I go back to our system that's monitoring all this, so what you're seeing are all of the 10 clusters, along with the management cluster. Okay. And what you're seeing is the blue dots are the management cluster. The 10 Kubernetes clusters are around them. And the white dots that are popping up in are the models that are being built live as I started building it. Okay. And the total number of services that are running to make this possible is well over 1,000 services. And the jobs, you can see the job count is actually going up live. Right. So it looks like the demo gods are smiling on us. Right. Now, we did build another case where 100,000 models were running live. And I wanted to show that system as well. And I'll come back and show you these numbers. And this is a case where all 100,000 models ran and completed. And I can go back to to this case. I reduce the speed a little bit and reduce the size also a little bit. So this is what a system that built 100,000 models look like. And this was run live. Right. Thank you. Very good. Now, if I go back here, you can see the models are still being built. It's still being submitted. And the interesting piece here is to get to this level of scale. You can see all of them have been submitted. Kubernetes is still responding and actually kicking off the jobs. So the load balancer here not only had to watch what is the load on the system, it also had to be optimized to the level where it's watching which of these clusters or which of these Kubernetes clusters are having a delay in responding back. So sometimes the Kubernetes API takes 2 seconds to give us a response back. So in cases like that, we won't necessarily go load up that particular cluster. We'll move the load to somewhere else. So it's not just that it's watching what is happening inside those clusters. It's also watching Kubernetes. Right? Now, you built all these models. You want to know what is the best model. So you can run a query across all of these models that just got built. And it'll come back and tell you that it's not just one answer. Right? So you need to know whether it's a best model based on root mean square error. That was what we showed on the UI. But you can also say there is a best model based on max percentage error or average percentage error, or any of the different percentage errors that you care about as a data scientist or as a subject matter expert as well. Right? And all of this, so this is coming live from the system that is actually running there. Right? And you can see the jobs are continuing to be submitted. There you go. OK. So we did show you real-world use cases that require a lot of scale. And getting to scale requires you to think slightly differently and also think about scale from day one. Thinking about scale at day 10 or day 100 causes a lot more angst than thinking about it at day 1. Right? And we had to learn that painfully on many of our applications as well. But what we showed you today was using Docker, Kubernetes, Kubeflow, GCP, NGC containers in a way that is significantly scalable. And it's definitely scalable, but it takes quite a bit of effort as well. So I want to end this with credits from the team that's listed here and many, many more who worked tirelessly for several years to get us here. So thanks a lot, guys. Thank you.